Assalamualaikum warahmatullahi wabarakatuh. We are from Group 8. We will present about monotone sequence, and the member of Group 8 is Maratun Solihah, Surya Samira, and Mirat Haisanov. Enjoy the presentation. Before we start our material, I will review the material from last week. Until now, we have obtained several methods of showing that a sequence x equal to xn of real numbers is convergent. The first is, we can use the definition of 3.1.3 or theorem 3.1.5 directly. This is often but not always difficult to do. The second is, we can dominate the absolute value of xn minus x by a multiple of the terms in a sequence an known to convert to zero and employ theorem 3.1.10. The third is, we can identify x as a sequence obtained from other sequences that are known to be convergent by taking Taylor's algebraic combination, absolute values, or square root, and employ theorem 3.1.9, 3.2.3, 3.2.9, or 3.2.10. The fourth is, we can squeeze x between two sequences that converge to the same limit and use theorem 3.2.7. The fifth is, we can use the ratio test of theorem 3.2.11.
Definition: let x equal xn be a sequence of real numbers. We say that x is increasing if it satisfies the inequalities x1 less than x2 less than xn less than xn minus plus 1 until blah blah blah. We say that x is decreasing if it satisfies the inequality x1 greater or equal x2 greater or equal xn or greater or equal xn plus 1. We say that x is monotone if it is either increasing or decreasing. Example: the following sequence are increasing like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or a power 1, a power 2, a power 3 until a power n. And the next example of the following sequence are decreasing, like 1, a half, a third, a fourth, a n. And the following sequence are not monotone, like plus 1, minus 1, plus 1. The sequence have a formula like minus 1 power n plus 1. And the last in the following sequence are not monotone, but they are ultimately monotone, like 7, 6, 2, 1, 2, 3, 4, and etc. (3.3.2) Monotone convergence theorem. A monotone sequence of real number is convergent if and only if it is bounded. Figure A. If x equal xn is a bounded increasing sequence, then limit xn equals supremum of xn that n equal of a natural number. B. If y equals yn is a bounded decreasing sequence, that then limit yn equals infimum of yn that n element of natural number. Proof. It was shown in theorem 3.2.2 that a convergent sequence must be bounded. Conversely, let x be a bounded monotone sequence, then x is either increasing or decreasing. A. We first start the case where x equal xn is a bounded increasing sequence. Since x is bounded, there exists a real number m such that xn less than or equal m for all n elements of natural number. According to the complementary properties 2.3.6, the supremum x stars equals supremum xn that n element of n exists in R. We will show that x stars equal limit of xn. If epsilon greater 0 is given, then x stars mean if epsilon greater 0 is given, then x stars minus epsilon is not an upper bound of the set xn that an element of n, and hence there exists xk such that x stars minus epsilon less than xk. The fact that x is an increasing sequence implies that xk less than or equal xn whenever n greater than k, so that x stars minus epsilon less than xk less than or equal xn less than or equal x star less than x star plus epsilon for all n greater than k. Therefore, we have absolute value of xn minus x stars less than epsilon for all n greater than or equal k. Since epsilon greater than 0 is arbitrary, we conclude that xn converges to x stars. B. If y equals yn is a bounded decreasing sequence, then it is clear that x equal minus y equals minus yn is a bounded increasing sequence. It was shown in part A that limit x equals supremum of minus yn that n element of n. Now, limit x equal negative limit y and also by exercise 2.4.4 b we have supremum minus yn that n element of natural number equal negative infimum of yn that n element of natural number. Therefore, limit y equals negative limit x equal infimum of yn that n element of natural number. Example A. Limit 1 over square root of n equals 0. It is possible to handle this sequence by using theorem 3.2.10. However, we shall use the monotone convergence theorem. Clearly, 0 is the lower bound of the set 1 over square root of n that n element of natural number, and it is not difficult to show that 0 is an infimum of the set. Hence, 0 equals limit of 1 power 1 per square root of n. On the other hand, as we know that x equal 1 per square root of n is bounded and decreasing, we know that it converges to some real number x. Since x equal 1 over square root of n converges to x, it follows from theorem 3.2.3 that x times x equal 1 over n converges to x squared. Therefore, x squared equals 0, whence x equals 0. Let hn equals 1 plus a half plus a third until 1 over n for n element of natural number. Since hn plus 1 equals hn plus 1 over hn plus 1 over n plus 1, greater than hn, we see that hn is increasing in sequence. By the monotone convergence theorem 3.3.2, the question of whether the sequence is convergent or not is reduced to the question of whether the sequence is bounded or not. Attempts to use direct numerical calculation to arrive at a conjecture concerning the possible boundedness of the sequence Hn lead to inconclusive frustration. A computer run will reveal the approximate values Hn is approximate 11.4 for n equals 50,000 and hn approximately 12.1 for n equals 100,000. Numerical fact may lead the casual observer to conclude that the sequence is bounded. However, the sequence is in fact divergent, which is established by noting that, like below, since Hn is unbounded, theorem 3.2.2 implies that it is divergent. This proves that the infinite series known as the harmonic series diverges. See example 3.7.6 in section 3.7. The term Hn increasing extremely slowly. For example, it can be shown that to achieve Hn greater than 50 would entail approximately 5.2 times 10 power 21 addition, and a normal computer performing 400 million additions a second would require more than 400,000 years to perform the calculation. There are blah 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 second in a year. A supercomputer that can perform more than a trillion additions a second would take more than 164 years to reach that modest goal. And the IBM Roadrunner supercomputer at a speed of a quadrillion operations per second would take over a year and a half.
Sequences that are defined inductively must be treated differently. If such a sequence is known to converge, then the value of the limit can sometimes be determined by using the inductive relation. For example, suppose that convergence has been established for the sequence xn defined by x1 equal to 2, xn plus 1 equal to 2 plus 1 over xn, n element of n. If we let x equal to limit xn, then we also have x equal to limit xn plus 1, since the one tail xn plus 1 converges to the same limit. Further, we see that xn greater than and equal to 2, so that x not equal to 0 and xn is not equal to 0 for all n element of n. Therefore, we may apply the limit theorems for sequence to obtain x equal to limit xn plus 1 equal to x plus 1 over limit xn equal to 2 plus 1 over x. Thus, the limit x is a solution of the quadratic equation x squared minus 2x minus 1 equal to 0. Since x must be positive, we find the limit of the sequence is x equal to 1 plus square root of 2. Of course, the issue of convergence must not be ignored or casually assumed. For example, if we assume the sequence yn defined by y1 equal to 1, yn plus 1 equal to 2yn plus 1 is convergent with limit y, then we would obtain y equal to 2y plus 1 so that y equal to 1 minus 1. Of course, this is absurd. In the following example, we employ this method of evaluating limits, but only after carefully establishing convergence using the monotone convergence theorem. Additional examples of this type will be given in the section 3.5. Let y equal to yn be defined inductively by y1 equal to 1, yn plus 1 equal to 1 over 4 times 2yn plus 3. First, we shall show that limit y equal to 3 over 2. Direct calculation shows that y2 equal to 5 over 4. Hence, we have y1 smaller than, less than y2, less than 2. We show by induction that yn less than 2 for all n element of n. Indeed, this is true for n equal to 1.2. If y key less than 2 holds for some key element of n, then y key plus 1 equal to 1 over 2 times 2y k plus 3 less than 1 over 2 times 4 plus 3 equal to 7 over 4 less than 2. So that y k plus 1 less than 2, therefore yn less than 2 for all n element of n. We now show by induction that yn less than yn plus 1 for all n element of n. The truth of this assertion has been verified for n equal to 1. Now suppose that yk less than yk plus 1 for some k, then 2yk plus 3 less than 2yk plus 1 plus 3. Hence it follows that yk plus 1 equal to 1 over 2 times 2yk plus 3 less than 1 over 4 plus 1 over 4 times 2y k plus 1 plus 3 is equal to k plus 2. Thus, yk less than yk plus 1 implies that yk plus 1 less than yk plus 2. Therefore, yn less than yn plus 1 for all n element of n. Since yn plus 1 equal to 1 over 4 times 2yn plus 3, the ninth term in the one trail y1 of y has a simple algebraic relation to third term of y. Since by theorem 3.1.9 we have y equal to limit y1 equal to limit y, it therefore follows from theorem 3.2.3 that y equal to 1 over 4 times 2y plus 3. The calculation of square roots. Example 3.3.5. Let a greater than 0. We will construct a sequence Sn of real numbers that converges to square root of a. Let Sn less greater than 0 be arbitrary and define Sn plus 1 equal to 1 over 2 times Sn plus a over Sn for n element of n. We first show that S square or n greater than and equal to 0 for n greater than and equal to 2, since Sn satisfies the quadratic equation s square n minus 2Sn plus 1 Sn plus a equal to 0. This equation has a real root. To see that Sn is ultimately decreasing, we note that for n greater than equal to than 2 we have Sn minus Sn plus 2 equal to Sn minus 1 over 2 times Sn plus 1 over a over Sn equal to 1 over 2 times s square n minus a over Sn greater than equal to 0. Hence Sn plus 1 less than Sn less than and equal to Sn for all n greater than and equal to 2. The monotone convergence theorem implies that S equal to limit Sn. Moreover, from theorem 3.2.3, the limit must satisfy the relation S equal to 1 over 2 times S plus A over S. Hence, it follows that S equal to A over S or S square equal to A. Thus, S equal to square root of A. Euler's number. Let an equal to 1 plus 1 over n power of n for n element of n. We will now show that sequence e element of en is bounded and increasing, hence it is convergent. If we apply the binomial theorem, we have en equal to 1 plus 1 over n power of n equal to 1 plus n over 1 over times 1 over n plus n times n minus 1 over 2 factorial times 1 over n square plus n times n minus 1 times n minus 2 over 3 factorial times 1 over n square and blah blah blah, and n times n minus 1 over n factorial times n 1 over n power of n. If we divided the powers of n into the terms in the numerators of the binomial coefficient, we get en 1 plus 1 plus 1 over 2 factorial times 1 minus 1 over n plus 1 over 3 factorial 1 minus n 1 minus 1 over n times 1 minus 2 over n plus 1 1 over n factorial times 1 minus 1 over n times 1 minus 2 over n 1 minus n minus 1 over n. We have en plus 1 equal to 1 plus 1 plus 1 over 2 factorial times 1 minus 1 and 1 over n plus 1 plus 1 over 3 factorial times 1 minus 1 over n plus 1 times 1 minus 2 over n plus 1 plus 1 over n factorial times 1 minus 1 over n plus 1 times 1 minus 2 over n plus 1 1 minus n minus 1 over n plus 1 and then 1 minus n over n plus 1. Note that the expression for en contains terms while that for en plus 1 contains n plus 2 terms. Moreover, each terms appearing in en is less than or equal to the corresponding term in en plus 1, and en plus 1 has one more positive term. Therefore, we have 2 less than and equal to e1 and less than e2 less than en less than en1 plus 2, so that the terms of e are increasing. Thank you for your attention.